Hey everyone, and welcome. We all know 5G is supposed to be incredibly fast, with connections that feel almost instant. But, that isn't magic. It's some seriously brilliant engineering. Today, we're going to pull back the curtain and look at the very core that makes it all work. All right, let's get right into it.
So just think about this for a second. When you're streaming a video or sending a photo, your phone is dealing with digital bits, ones and zeros. But radio waves, they're waves. They're analog. So how in the world does your phone translate the language of computers into the language of the airwaves? That is the big question we're going to answer today.
Behind all the promises of 5G, the crazy speeds, the low latency, connecting everything, there is this critical, totally invisible engine doing all of the heavy lifting. It's really the unsung hero of all modern wireless, working behind the scenes to make everything happen.
And that hero has a name. It's called the physical layer, or 5 for short. Now, this is the term you really want to remember, because it is the absolute bedrock of how 5G and really any wireless system works. It's the part that's closest to the actual hardware, the point where the digital world literally meets the physical world.
So what's its job? Well, in a nutshell, you can think of the physical layer as the ultimate translator. It has this incredibly important task of being the bridge between two completely different worlds, the digital data that's inside your phone and the radio signals that fly through the air.
So yeah, here it is, basically its official job description. The fuzzy layer grabs your digital data, converts it into radio signals to be sent out, and then, on the other side, it catches incoming radio signals and turns them back into the exact original data. Without that perfect two-way translation, nothing works. Simple as that.
Let's break that mission down into 4 really clear steps. First, it converts the digital data. Second, it transmits the radio signals it just created. Third, it has to listen for and receive incoming signals. And fourth, the magic step. It recovers the original data from those signals. It's this perfect loop that's happening millions of times every single second.
Okay, so to do this super complex translation job at 5G speeds, the physical layer needs a pretty powerful set of tools. You can think of it like a specialist's toolkit, just filled with these highly advanced technologies designed for one single purpose: getting data through the air as efficiently as humanly possible. The very first and maybe the most important tool in this box is called OFDM. It stands for Orthogonal Frequency Division Multiplexing. Yeah, it's a bit of a mouthful, I know, but the idea behind it is just brilliant. This is the core technology that lets 5G handle enormous amounts of data without everything just turning into a jumbled mess.
So, why is OFDM such a big deal? Well, instead of trying to shove all the data down one gigantic single-lane road, OFDM cleverly splits the available radio frequency into thousands of smaller parallel subcarriers. Think of it like a massive highway with thousands of individual lanes, instead of just one big one. This makes the whole system way more resilient to problems like signal reflections and interference. It basically prevents data traffic jams.
All right, next up is a concept that's pretty unique to 5G, and it has a kind of funny name: flexible numerology. What's really cool about this is that it's built on the idea that not all data is the same. I mean, streaming a 4K movie has totally different needs than, say, a self-driving car sending critical sensor data. Numerology is basically the setting that adapts the signal to fit the specific job.
And you can see exactly how it works here. By changing the spacing between those little subcarrier lanes we just talked about, 5G can optimize the signal. If you use a wider spacing, like 60 kHz, you get incredibly fast, low-latency communication, perfect for those critical applications. A narrower spacing is great for just your standard everyday data. This flexibility is a huge game changer for 5G.
Okay, tool number 3 is channel coding. The simplest way to think about this is as error-proofing for your data. I mean, the airwaves are a noisy, unpredictable place, and data can easily get corrupted. Channel coding adds some clever redundancy to make sure the data that arrives is exactly the data that was sent. And what's neat is that 5G uses one powerful type of code for your actual data, your videos and messages, and a different, super reliable code for the essential system commands that keep the whole network running smoothly.
And, believe me, the toolbox has even more. We've got MIMO, which stands for Multiple Input, Multiple Output. This is all about raw capacity. It uses multiple antennas on both the cell tower and your phone to send way more data at the same time. It's like adding even more lanes to our data highway. And then there's beamforming, which is so cool. It intelligently focuses the radio signal directly at your device, kind of like a spotlight, instead of just broadcasting it out in every direction. That's what gives you a much stronger and more reliable connection.
So we've got all these amazing tools, thousands of subcarriers, multiple antennas, focused beams of energy. It sounds like it could be total chaos, right? Without some kind of master plan, it would be. So 5G needs a system to map everything out and keep it all organized.
And that system is called the resource grid. This is the master plan. Honestly, the best way to picture it is like a giant spreadsheet or maybe a checkerboard. Every single little piece of data gets a very precise address on this grid, so the transmitter and the receiver know exactly where to put it and, more importantly, where to find it.
So if you look at this grid, the columns going up and down are all about time. Each column is a tiny, discrete moment in time, technically called an OFDM symbol. This organizes all the data chronologically, telling the system when each piece of data is being sent. And the rows going across the grid, that's all about frequency. Those are our OFDM subcarriers, our individual lanes on the highway. This tells the system which lane each piece of data is traveling in. So you've got the when in the columns and the which lane in the rows. Every single packet of data gets a unique time and frequency coordinate. That's how the whole system stays so perfectly organized.
Okay, I know this has been a lot of theory. We've talked about tools and grids and layers, but let's bring it back to the real world. Where does all this incredible technology actually live and do its job?
Well, the physical layer is running in two main places you interact with every day. In the 5G base stations, the cell towers, which are often called GNBs, and it's right there in your pocket inside your smartphone's modem. But, and this is really crucial, for the engineers and researchers who are designing what's next, it's also implemented on things called software-defined radio, or SDR platforms. Think of an SDR as a totally flexible, programmable radio that lets them experiment with the PHY layer directly in software.
So at the end of the day, here's what it all boils down to. The 5G PHY layer is the true foundation. It's this amazing place where super complex digital signal processing meets the real-world physics of radio frequency transmission. It really is the engine that powers our entire connected world.
And that brings us to one last really fascinating thought. These platforms, like software-defined radio, they treat the physical layer not as some fixed piece of hardware, but as flexible software. So if we can literally program radio waves like we write code, what could the future of wireless communication even look like? What will the PHY layer of 6G and whatever comes next be able to do? That's the real frontier of wireless engineering, and it's something to think about. Thanks for joining us for this explainer.